So next up, we have Ben Kuster to talk about how the free and open source VC map framework and Cesium can come together to visualize panoramic images and integrate it with 3D and 2D data in a single application. So over to Ben. Thanks.
Thank you. So my name's Ben, and I'm going to talk to you about the Virtual City Map. I work for a company called Virtual City Systems, 20 years going, so also been around for a while. I work in Berlin, and we mainly focus on 3D city models, and have a lot of knowledge on city GML. That's what we focus on. And what I'm here to talk about is how some of our customers have panoramic images coming up, and they want to be kind of vendor agnostic when it comes to viewing them, and they also want to view them in the context of their already existing geographic data. So what we maintain is an open source project called the Virtual City Map project. It consists of two libraries, a GIS core, which does all the core stuff, and a UI framework on top of that that lets you plug in stuff. And the idea behind it is that it's an abstraction layer on top of well-known open source projects. One of them, Cesium, we've been using since, I think, 2013, 2014, so a very long time, for our 3D maps and our 3D data, and open layers for 2D. And we also have an oblique imagery viewer, also based off of open layers. And it should be light to use so that people working in administration without any coding knowledge can kind of plug together a map and deploy it in a browser to their customers or colleagues. And if they want to get really into it, there's a plugin interface where we can just plug in almost any GIS idea. We use that a lot for research and development features. So I just saw a demo from a colleague. He's working on a plugin to simulate how snow piles melt. So that's not a use case we have a lot in Germany, but they do in Norway, I guess. So I'm here to talk about high-resolution panoramic images, 2D technically, right? So they're captured in a 360 view, mounted onto a vehicle. Most of the time, they're very specific on how they have to be mounted, but newer systems are coming out that are very cheap and very easy to just mount onto basically anything. And what happens is you get an equirectangular image that represents the entire sphere where it was captured. And most of the time, they will also deploy a scanner, a laser scanner, with the vehicle, so you also get a point cloud as you drive through the city, which is going to be important coming up. So that kind of describes what these images are, right? And the reason they use these is that they give you a very street-level view, and we all know this from Google Street View, right? And you can do a lot of stuff with that, especially if you're trying to monitor your city as a municipality. You can do change detection, you can do documentation on infrastructure and construction, and what I've been talking to some of our customers, we're thinking about, well, if we mount these onto vehicles that belong to the municipality that drive around the city anyway, we can do almost real-time analysis of where we have to do work. Trees, signs, markings, they're trying to do like lane signs and try to figure out where they have to do maintenance in their city just by scanning the city every week or something like that. And instead of doing like an image campaign like Google would do once a year or every other year, they just mount it onto a vehicle and then they get certain streets every day almost. So these are kind of the challenges we were facing. It's a large amount of data per image. To stream into a client, you have to think we always have a web client. And there's going to be a large amount of images depending on the campaigns. And if we're talking about images coming in every day, these are just going to grow. And somehow we have this equirectangular image that looks kind of funky. And we need to display it to the human so he can actually navigate inside it and kind of get a feel for that. So we thought of some concepts on how we can handle that. And these are basically tried concepts we already know from any geospatial format. So images, if they're too large, you tile them, right? You can make them small or like into chunks. For large amounts of points, you need to index them. So every image is taken at a certain location, and you can index that. So you can query it, and you can somehow place points in your vicinity while you navigate the map. That's fairly standard. And we need to display it in a web client, and obviously we're going to use the 3D rendering engine we already have. We're going to use Cesium.js for that. And that's basically what we came up with. So the solution is we're going to use cloud-optimized GeoTIFF as like the base format for the images. The reason being, if you do like classic tiling, you get millions and billions of tiny files. Serving those and pushing them to the cloud is a pain. So we opted to not do that very early on and said, I don't want to do that anymore. So we're going to use GeoTIFF for this, cloud-optimized GeoTIFF. And we're going to use a FlatGeobuf, which is also cloud native in a way that you can query it. It's a file. It's a static file. And that kind of gives us an extra edge because using FlatGeobuf instead of something like a WFS or even a custom service to index and query the points, we just have a file. So you have to host a file and you're done. You don't have to have a backend service. And we're going to use Cesium.js to render the sphere because, well, we already have that, right, in our solution. So this is kind of how we structure data. For anybody who doesn't know how tiling works, that's an image I got off the OTC. That's basically how tiling works. And the GeoTIFF, cloud-optimized GeoTIFF profile just allows you to store all of those pyramids in one file. So you upload one file to the cloud, and you can query it using range requests, and that is very performant. Also very performant in upload, because you only got that one file to upload. And because it's an equirectangular image, it actually represents a sphere. So we can even just define the tile matrix that we're going to use. So we don't have to do any custom tile matrix stuff. It's just we're using the CRS84 quad tile matrix set, which just defines the entire globe with 2 level 0 tiles. And this is, at the bottom, you see there's additional information that we get from the laser scans. So if you have a point cloud with the laser scans and you place a camera at the same location that the car was when the image was taken, you can get intensity information and depth information off of your point cloud. And we also store that in a file, and we also tile that, and we also serve that. And all the images for your campaign we put into a FlatGeobuf file, place it next to it, and push it to the cloud. Right. And then we provide some meta information because we kind of have to extend what GeoTIFF provides to kind of give information on the image. So we need to know where the image was taken and if it has additional information and the orientation of the camera at the point in time where this image was captured. And this allows us to place the camera in Cesium at exactly the same location as the car was in 3D space and render a sphere where we then project the image onto. So we're going to use the GDAL metadata properties bag, which kind of exists through GDAL. So we have a well-defined place in the GeoTIFF header where we're going to store our information without clashing with anything, hopefully. And we kind of wrote documentation on this. The idea is this is supposed to be an open data specification. We've only used open standards so far, and we're just trying to add a bit of meta information to make it run smoothly in the client. And this brings us to like that one major goal that our customers had, which is it has to be vendor agnostic. They don't want to have to deal with only Trimble software or Hexagon or whatever. They want to be able to throw in any vendor, transform it into this open standard, and use it in the client. And this is basically what it looks like if you have the raw data. You get an RGB image. That was kind of clear. That was the picture taken. You get depth information if you have a point cloud. And you get an intensity image, which is just a different view on the point cloud, and it was a customer requirement that we have this. All right. And now we need to render it, which is kind of a different challenge. So we have the data, it's structured, it's hosted, and now we need to stream it into the client. So one thing is that the camera is looking outward, and we need to render a sphere, because that's what it captured, and we need to render it into the sphere which isn't really the way you usually do it. You render it onto the sphere, right? We're looking from the other side now. Somehow, we also need to stream the data, so we don't pull in those 20 megs on every image, because bandwidth with municipalities in Germany isn't that wide. And we want to give some feedback to the user to get that 3D feel. Because it's just 2D information right now, but because we have the point cloud and we have the depth information, we can kind of give some feedback to the user on how the depth would look. Right, and the last point is that we kind of also want to integrate other 3D data the customer already has, or that the customer creates within the map. So you can draw stuff and measure stuff in the map, and we kind of want to render that into the image as well. And the solutions we have, this is kind of technical, a lot of information. I'm going to go through that really quick. But Cesium already provides us with a lot of these things. So rendering into a sphere is actually not that difficult. You can render a sphere, and you can use an ellipsoid where you can define the opening and the height of the sphere that you're rendering, and you create a wedge. So we've tiled our image, and every tile we render into a small little wedge, depending on the level. And then we create two coordinate systems. So we create a coordinate system that represents the sphere that we're projecting into. And we can transform from the global coordinate system, which Cesium uses, into that Cartesian system of the sphere, and then into the spherical system of the image itself. If you remember, we tiled it using the CRS-84 tile matrix, and then we can actually really pinpoint where every tile needs to go onto which wedge in 3D space. And since we're only rendering a small portion at a time, we can stream the data into every one of those tiles. And additionally, so what we did is we extended the material texture in Cesium to be able to add multiple textures to the same material as they load. And we can provide the depth information just as an F32 texture, not really supported by Cesium natively, but it's supported by WebGL, so there was a way we could work around it. So the material that renders the wedge has the information on the depth at that position, and we can attach the cursor's window position to that information as well. So we can render a cursor. I'm going to show you in a bit. It makes more sense then. To show the user how the 3D scene actually works into the image. And since we're using Cesium.js, we can just integrate other data sources into the same scene, render the sphere, and just place the 3D information within. The last challenge we kind of had was determining which tiles to load at which position. So we have the data structured, it's served, and the client is able to render parts of the image and request parts of the image. So we need to determine level of detail, and we need to determine which tiles to render. So what we did, it's kind of cheating in a way. We just take the camera center and we determine the number of pixels on the sphere and the number of pixels on camera, on the screen, and then we determine level of detail, and those are just the images that we're going to load for the entire scene. And depending on the field of view, we can intersect the field of view with the unit sphere and then determine which tile coordinates to load, because we can transform from the global coordinate system into the sphere's coordinate system that we're projecting onto. And here I have a live demo. I was warned about this, so being a developer, I have a local server running, and that should look like this. So this is basically our solution. As you can see, there are multiple maps available to us. I'm just going to be using the 2D map because it uses the least bandwidth. And I have some local test data that we can look at. I can jump into a scene like this and move around fairly smoothly. And as you can see, this is what I was talking about. This cursor at the position basically gives you depth, the feel of depth, and how the image is structured in 3D space. And using some shader magic, you can actually see this information as well and kind of blend it over your RGB information. This is important because we're trying to facilitate the user with the capability of measuring in just the one image. So instead of having to have 2 images and 2 key positions to measure something, you can do this in 1 image because you have the depth information you can calculate backwards. If you have the distance to the camera and the position on the unit sphere, you can generate a global position for a pixel in the image, right? So you can measure in 3D space in this image. But sometimes the camera and the laser scanner, they aren't aligned perfectly, so that's why we can overlay this other information of the depth image so that you see what you're actually measuring. Yeah, that's about it. All right. Oh, this was my backup. All right. So what we plan to do now, and this is what we're looking at right now, is trying to integrate 2D data that you have. If you use a terrain and you drape the 2D information onto the terrain, it's not going to look nice in the sphere because the terrain will cut the sphere in half. But if we can use what we do now for 2D vector features into Cesium 3D primitive conversion in the same fashion, but use a terrain to place the positions absolutely, we're looking at rendering primitives into, it will look like they're inside the image. And in a way, we've already started doing this for points. They're not on here, let's see. As you can see, this is the footprints. These are the footprints of the other positions, and we kind of render them in here as well. There's a certain height offset issue that we're having right now, which we're trying to fix by just placing them onto the terrain. So typically, customers will have some quantized mesh that we can place the features onto before we render them into the scene, and then it will look smooth in the image, right? That's what we're trying to get to. Also, more support for 3D tiles, so that you can render 3D tiles directly into the image, but only if they're within the bounds of the image. And that is something that I haven't figured out how to do yet. We're also thinking about maybe rendering the terrain into it, but make it transparent. And maybe you can render imagery into it as well. So if you have analytics, say flooding or whatever, that you want to see in your panorama image, you could render in the globe and drape imagery on it. And models, that is something the customer wants, is that they're able to place architectural models and then have a street view where you see the architectural model in the street view. That is something in my head that makes sense, so I can use the depth information and maybe hack the Cesium depth buffer in a way that occlusion happens based on the depth information in the panorama image, so that if I place a 3D model behind a building and it rises above it and I see it from street view, that Cesium will render the building through the image, but only where it's not occluded by an image that is already present in the image. Building that's already present in the image by using the depth. I don't know how that works, but I think it should work. If you do know how that works, talk to me and tell me how. That would be great. Yeah, this short acknowledgement project was funded by 2 municipalities in Germany, Hanover and Rostock. And we have a partner that does most of the data wrangling called Point Cloud Technology. And the images were provided by the city of Hanover. Thanks.